Good afternoon, everyone. My name is Yue Li. I'm a PhD candidate from the University of Amsterdam. Here I present our work titled Chorus, Multi-Teacher Pretraining for Holistic 3D Gaussian Scene Encoding. This is a joint work with my colleagues from ETH Zurich, Insight, and University of Trento. For 3D, many of us want a similar backbone as of dyno model for 2D that are pre-trained from a large scale of 3D scenes, transferable across different tasks, and reusable for different 3D data formats. Here, we take one step back and think, instead of relying on 3D self-supervision alone, is there a different route we can explore for scalable 3D pre-training? But first, where could the scalable 3D input come from? One emerging substrate is high-fidelity renderable 3D worlds. With 3D Gaussian splatting, large real scenes can be turned into immersive 3D spaces. And these spaces are becoming easier to capture, to generate, and to interact with. For us, they are not only just rendering outputs, they are training substrates for 3D representation learning. This is the line of work behind Chorus. The goal is to turn renderable 3D worlds from things we reconstruct and showcase into transferable 3D scene embeddings that could be used for 3D understanding. We started with object-level Gaussian encoder in shape splat, moved from objects to indoor scenes, and started using a 2D teacher in scene splat. Then we enlarged the data and established the benchmark for data-driven Gaussian scene encoder. And Chorus sits in the line next. Here, we made a deliberate change. Earlier in this line, we mainly explored self-supervision. And in Chorus, we part from 3D self-supervision and ask whether multiple 2D foundation models, they can help us build a strong 3D scene encoder. Why this different route? We will justify it later in experiments. Together, for the Chorus line of work, our goal is really to learn a general-purpose 3D scene encoder from the renderable 3D worlds. Our previous work, Scene Splat, showed that direct feed-forward encoding of a complete Gaussian scene is possible with the output feature of language-aligned features with which we can use for scene query. But for Chorus, we wanted to go beyond this setting. Scene Splat is mainly optimized for open vocabulary semantics. Its features are not yet a strong scene embedding, and its encoder often have tens of thousands of tokens at its final stage. Chorus addresses this by using the multi-teacher framework, portraying a holistic 3D scene encoder that transfers across different tasks, not only segmentation. These are the three teachers we use. SIGLib2 gives language-aligned semantics, and DynoV3 provides general visual structure, and pSpatial gives object-level local cues. The name Chorus is meant to capture this idea. Multiple teachers, but one unified 3D scene embedding. Here is a Chorus pipeline. Step one is the training data preparation. For each Gaussian scene, we run the 2D teacher on the training views and get each 2D feature maps. Then using the same rasterization weights from 3D.js rendering, we lift the 2D features back to individual Gaussians. Step two is our 3D encoder training. The input to Chorus is Gaussian scene itself, that are centers, colors, opacity, scale, rotation. The encoder produces compact scene tokens, as well as per Gaussian embeddings. That is the representation we will reuse downstream. Because the teachers have different feature spaces, we do not force all supervision in one output hat. Instead, a shared encoder-only 3D backbone learns common scene vectors, while lightweight teacher-specific projectors align the backbone embedding in SIGLib, Dyno, and pSpatial with multi-teacher alignment losses. With small task-specific decoders or modules, the embedding supports open vocabulary queries, semantic segmentation, instance segmentation, and visual question answering. So the method is simple at high level. prepare Gaussian scenes, lift 2D teacher signals based on the training views, then train one native 3D Gaussian scene encoder, and transfer the resulting scene embedding. Now let's see whether embedding are actually useful. The first evaluation is open vocabulary 3D semantic segmentation. Here, the encoder produces language-aligned scene features, and we query them directly by text labels. Course improves over scene splat over all 4 benchmarks here. To make the embedding visible, this demo shows PCA view of the encoded language head features on a novel scene. Course produces cleaner object-level structures. For example, here, plants and tables, they are separated more coherently. This is a qualitative sign that the encoded features are more semantic aware and separable. Here is a second novel scene where the same PCA view is shown in a concert hall. Again, Course gives more consistent regions for chairs, stairs, floors, etc. Let me come back to the earlier question, why we take the different route of multi-teacher pretraining. So we compare here course pretraining with self-supervised pretraining under the same number of input scenes. The gap is large right from the beginning. On the linear probing performance of the trained encoder, all the way up to using 3,500 training scenes. So the message is clear. At the current data scale we manage, multi-teacher pretraining is a much stronger and faster scaling route. In the ablation, we show that the gains and generalization are consistently driven by the added teachers. Come to the application of course encoder. We plug course into Gaussian VLM, replacing its previous 3D encoder with course, and rerun the same instruction tuning. Because course provides more compact scene tokens, the VLM becomes much simpler. It uses fewer tokens, trains nearly twice faster, and the VQA performance improves overall. There is one more thing here. So far, course is introduced as the 3D Gaussian splatting scene encoder, but what if we remove most Gaussian-specific parameters and keep only point-like attributes that are centers, colors, and normals? When doing so, we keep the same multi-teacher objective. What came out of this is unexpectedly strong. With only these point-like inputs from the splatting data, we end up have a state-of-the-art point cloud encoder. On point cloud benchmarks, the course variant outperforms Sonata in linear probing, especially on Scannet 200 and Scannet++. It also remains competitive in decoder probing and full fine-tuning. And importantly, it achieves so while using nearly 40 times less training scenes. So the surprise here is really the same teacher-driven framework can produce strong point clouds encoder using the splatting data. But why does course transfer to point clouds at all? Our interpretation is on feature-level robustness. Pretraining with Gaussian data acts like a structured augmentation for point cloud input formats, while the teachers impose semantic and object-level grouping. The UMAP visualization here shows that course feature forms more compact and well-separated clusters on different instances. We test this robustness directly. Course retrieve the same noisy instances more reliably in the perturbation experiment. And on the iPhone RGBD capture data, it remains above Sonata as well. Together, these two tests show that course point cloud features can preserve instance identity and a semantic structure on the noise and capture shift. Let me close with the main message. Course suggests a different route towards a general-purpose scene encoder, using renderability as a bridge, and multi-teacher supervision as the efficient signal, and learn scene embeddings from the renderable 3D worlds. Here, we use Gaussian splat as the substrate, but any future 3D data format that are renderable can become a natural choice for teacher-driven 3D pretraining. With this, I conclude. Please come and chat. Our poster number is at number 1. Thanks for your attention.